Good morning, good afternoon, good evening. Welcome to our second Transition podcast. My name is Daniel Palmer and I'm the Deployment Manager at OGCI Climate Investments. Today, I'm delighted to be joined by Stephane Germain, a CEO and founder of GHGSat, one of our methane detection portfolio companies and a global leader in greenhouse gas emissions monitoring. And also Dr. Robert Kleinberg, Distinguished Senior Research Scholar at Columbia University's Center on Global Energy Policy. Today we're going to be discussing monitoring methane emissions with satellites, what's currently possible and what this holds for the future. I'm really excited about what's happening in this area right now. We've had enormous progress in 2020 and I think 2021 is going to be a very exciting year for that. So with that, I will introduce Dr. Kleinberg, and they've just published a paper on satellite monitoring of methane emissions, and he's going to start with sharing some insights from that. So over to you, Dr. Kleinberg.
Well, thank you, Daniel. It's really a pleasure to participate in this Oil and Gas Climate Initiative podcast. Really a pleasure and honor to be here. It's often said that methane is the second most important greenhouse gas after carbon dioxide. But in a way, that's really not true because once you emit carbon dioxide into the atmosphere, it tends to linger there for centuries. And so even if we stop emitting carbon dioxide today, we're still going to have an increase of temperature for decades and indeed centuries to come. So if you really want to mitigate global temperature change in, say, a 30-year time frame, as is now the current ambition, you really need to be looking at methane because methane doesn't stay in the atmosphere so long. Its lifetime is a few decades. So once you stop emitting it, the concentration of methane goes down and the Earth stops heating and indeed will slightly cool off a bit. So really, controlling methane is the fastest way to slow down global climate change. So it is really important. Now, there are multiple sources of methane. About half the methane that goes into the atmosphere is from natural sources, swamp gases, seeps, and so on. The other half is roughly equally divided between agricultural sources, which is principally livestock herds and rice fields. About a third comes from waste, such as landfills and wastewater treatment plants and the like. And then roughly a third from fossil fuel sources, and that's coal mines plus oil and gas development. So those are the three sources. And indeed, all the anthropogenic sources have large emitters that are detectable from satellites and other platforms. So one question that comes up is, why do you need satellites? There's other ways of detecting methane. Anything with an infrared camera will do it, and that could be in aircraft or ground-based measurements. But the thing about satellites that are really unique is that they go everywhere all the time. This problem of methane emissions is a global problem, and every country has to really cooperate and participate in this effort. But let's face it, there's a lot of countries out there that are not particularly friendly toward having aircraft flying over their oil and gas facilities, for example. Whereas once you launch a satellite, it can go anywhere it wants. It goes everywhere, sees everything. So the measurements are global. They're also frequent. And we'll talk about this in detail in a minute. But basically, satellites will pass over have the capability of passing over any point on Earth every day. And that is far different than, say, an aircraft deployment where really it's only practical to fly an oil field perhaps once, maybe a few times a year. Same is true of trucks and so on, truck-mounted sensors. So satellites give you global and frequent measurements, and they also have a uniform quality control in the sense that it's one platform that's giving you measurements everywhere, and the data is being interpreted by an international team of scientists typically. Whereas where you have a ground-based measurement, you're subject to problems of calibration and bias and, let's face it, operator error and inattention. So satellites really have those unique and helpful capabilities. And that's one reason why we at Columbia University titled our report on satellites, on satellite detection of methane, "No Place to Hide." Now, who are the users of these data? Well, governments are important users because almost every government on Earth has committed to the Paris Agreement and has signed up for nationally determined contributions, which basically are promises to limit the emission of greenhouse gases into the atmosphere, and that's principally carbon dioxide and methane. So governments and international agencies want to know whether these nationally determined contributions are being adhered to. Um, Another interesting group of users are companies themselves. So, for example, if you're an oil and gas company, you sell natural gas, of which methane is the primary component. But leaks can develop perhaps out in a remote and infrequently visited location, somewhere perhaps on a pipeline. When you have satellite measurements, that gives you the opportunity to see that you're losing methane. And believe me, there have been some really gigantic methane losses from gas companies, quite remarkable actually, in recent years that have been found in this manner. Non-governmental organizations like environmental advocacy organizations are clearly interested. They're concerned about climate change. They want to know where the problems are and how best to solve them. So they are important users. Finally, and sort of most interestingly, is the latest group of users, which are investors. Investors are now increasingly interested in making investments in companies that are not going to be subject to regulatory and reputational risk as problems of climate change and other similar environmental issues become more prominent in public thinking. So what we're seeing now is rating agencies developing what are called ESG ratings, and this is environmental, social, and governance ratings, which basically measure whether your company is a good global corporate citizen or not. And right now, there's a lot of effort being put into devising these ratings. They are best based on good, solid data, and certainly greenhouse gas emissions constitute a very important part of that picture. Now, what is the nature of these satellite systems? I'm going to review a couple of them. The first sort of class of satellites are what you might call sort of global everyday platforms. And this is best exemplified by the Sentinel-5P satellite launched by the European Space Agency. On it is a sensor called TROPOME, which is the methane sensor. And this type of satellite indeed flies over every point on Earth every day. So it's got great spatial and temporal continuity. It does have limitations. Because the swaths are big, sensitivity is not particularly good. So for the TROPOME sensor, point sensor sensitivity is something like 5 tons an hour. And believe me, 5 tons an hour is a pretty giant leak. We do see them, but they are really on the high side. Spatial resolution, roughly 7 kilometers pixels, so 7 kilometers on a side. So not terrific spatial resolution. They have problems of being interfered by clouds. So, for example, if it's a cloudy day, these sensors really just don't work. And I can tell you, I'm in Boston now. It's about 1:30 in the afternoon, so TROPOME is overhead. However, it is overcast, so it's not seeing any methane emissions from my metropolitan area. A fourth factor limitation is what's called albedo. So these satellites require a good infrared reflective surface on the Earth, and most Earth surfaces are pretty good infrared reflectors. So that's not a big problem. But water in particular is not. So these satellites do not work over ocean. Fortunately, there are not many big methane emitters at sea. So that turns out not to be a huge problem. It is somewhat of a limitation. So that's the first kind of satellite sensor, which is basically the global everywhere. Second type is represented by MethaneSAT, which is going to be launched in the next year or two by the Environmental Defense Fund. Quite remarkable, a environmental advocacy group will have its own satellite paid for by itself. It's got about 10 times better sensitivity than the Sentinel-5P. It's got about 10 times better spatial resolution. Therefore, cloud interference will not be quite as big a problem for them. However, because it's more tightly focused, it does not image every point on Earth every day. It's going to have a limited target list, so you have to specify latitude and longitude where the satellite can be looking as it flies overhead. And MethaneSAT people tell us that they will be able to measure about 200 targets a year. Now, 200 targets, that's a substantial number, but compared to the 1 million oil and gas wells in the United States alone, compared to the hundreds of thousands of miles of pipeline, 200 is a modest number, and the Environmental Defense Fund tells us that this is basically to accumulate science information, and that's fine. That is a limitation for them. So just to sum up my remarks, I think we need to think about satellites as part of multimodal surveillance regimes. Different kinds of satellites are going to be interacting with each other, and each system will have its own strengths and weaknesses, and Stephane is going to tell us more about that later. There's also going to be integration with aircraft platforms, which are much more sensitive, but again, are not available all the time. There's going to be ground-based sensors, mobile sensors, permanent sensors, all are going to play a role in really what has to be this global effort to limit greenhouse gases. So with that, I'm going to turn it back to you, Daniel, and looking forward to the further discussion.
Thank you very much, Dr. Kleinberg. Appreciate that input. So next we're going over to Stephane, who's the CEO of GHGSat, and they recently launched their second satellite, and I would say progressing leaps and bounds with commercial methane satellite imagery. So with that, over to you, Stephane.
Thanks, Daniel. I appreciate the opportunity to chat with you and Bob today. I think it's very exciting to see all that's going on in the methane measurement and detection world. I think that's amazing to see the pace with which things are evolving, and it's great to be part of it. So let me start by describing how our satellites fit into the mix that Bob just described. If we go back to that table as it was set earlier, there are global everyday mappers, so satellites like the European Space Agency's Sentinel-5P. There are what I would call area mappers, which are satellites like the one planned by MethaneSAT, where it's taking the resolution down a notch so you can see smaller areas, but perhaps with higher resolution. And then finally, if you take it one step further, that's where we sit with spot measurements. And so that means that each one of our measurements is approximately a 12 by 12 kilometer photo of the surface of the Earth. So we take a snapshot here, and then we take another snapshot over there. And as we fly over Florida, we take a snapshot. As we fly over Central America, we take a snapshot. As we fly over Ecuador, we take another photo, and so on. So we take snapshots as we go along in our orbit around the Earth. The way the satellites work is really important because it explains how these different systems can be used together. So if you bear with me for just a minute, I'll explain that each one of our satellites is in what's called a polar sun-synchronous orbit. So our satellites go north-south, about 15 times a day. We go around the planet in about 98 minutes. And the Earth turns underneath the satellite as we go north-south. So the Earth turns east-west as we go north-south. So we take about 15 slices of the Earth every day. And if you do the orbital mechanics and look at the various technical parameters of the satellite, it turns out that each one of our satellites can see any point on the surface of the Earth approximately every 2 weeks. So compare that to the everyday mapping of TRPOMI or the periodic mapping that'll be possible with MethaneSAT. We're more limited, but in the sense that we only come back with every satellite every 2 weeks. But what we get as an advantage for that is that we can now see with super high resolution compared to some of these other satellite systems. So whereas TRPOMI has approximately a 7 by 7 kilometer pixel, we have a 25 meter by 25 meter pixel. So we can see individual facilities. The other thing that's really important to point out is that TRPOMI cost about €500 million to build. So really, it's only national agencies or pan-national agencies like the European Space Agency that can afford to build that kind of satellite. MethaneSAT, by public reports, is somewhere in the $100 million range. So for an NGO, that's really impressive. I tip my hat to the Environmental Defense Fund for having raised that much money. It's a heck of an investment for a single satellite. Our satellites cost a tiny fraction of that. And so we make up for the fact that we have spot measurements by adding more satellites. We can build hundreds of satellites for the cost of one TRPOMI satellite. So we still won't map the whole planet every day, but there's lots of places in the world that we don't necessarily need to go monitor if you're looking for industrial emissions. Going to look at the middle of Greenland isn't really going to help you when you want to look for landfills or even oil and gas. So our system is designed specifically to look for facility level industrial emissions and to monitor those with very high precision or high resolution and high precision. And that's the difference. And these satellite systems are all important. And in a wonderful way, they're actually all complementary. So today we use global measurements from TRPOMI to identify hotspots that we then go and take a look at with higher resolution with our satellite. And we've been doing that with TRPOMI for years now. We even published a paper about it in 2019 about a series of sources in Central Asia. And we're very much looking forward to doing the same thing with MethaneSAT. And there's even more satellites that have various complementary capabilities, like flaring detection on a satellite operated by NOAA. So there's all kinds of complementary capabilities. But at the end of the day, what our satellite does that's really different is this facility level monitoring. So we monitor about 100 times higher resolution, and we can detect leaks that are about 100 times smaller than satellites like TRPOMI or actually even others that might have some sensitivity to methane. So that's where we position ourselves in the range of satellite technologies that exist today. And it's really a pretty unique niche. There's nobody else that does it today in the world in the same way that we do. And that gives us a great commercial opportunity. That's why we've been building our satellites. We launched our first one in 2016. And we just launched our second one, our first commercial one, about 2 months ago. And the results from that satellite are really exciting. So we took everything we learned from our demonstration satellite and we corrected, adjusted, improved, amplified. Pretty much all of those words can be applied to our second satellite. And now we're really pleased to be seeing results that are about 10 times better on our satellite that just launched compared to a demonstration satellite. So we can see leaks that are about 10 times smaller. We're seeing where we used to see one emission from one really big source, we'll now see 5, even 10 little plumes, little emissions in the same area as that one big source. Where we used to see nothing, we now see small plumes where they together can accumulate to be a hotspot that would be detectable by TRPOMI, for example. So these different capabilities, as I said before, complement each other. And the results we're seeing from C1 bear out the value proposition of having these various systems working together and being able to integrate all that information together into a common view that's basically abstracts all the technical detail and all the rocket science and presents at the end of the day emissions and source detections and leak detections for our customers. And it's that kind of aggregation that led us to publish just a few weeks ago a new representation of global global methane data, which is a global map of methane concentrations that we call Pulse. And that map is designed to advance the state of the art. So it provides now a global view of methane on a 2 kilometer by 2 kilometer grid scale. And it's updated every week, and it's available for free. Now, I want to be really clear, it's not just our data. Quite the opposite. It's actually right now primarily driven by data from Tropomi, from Sentinel-5P, because they cover the whole world and therefore can have data from most of the world. But we inform and adjust that data using data measured by our own satellites and actually from third-party satellites and third-party data. So that's all bundled into what's presented in this map. And it's deliberately done at a scale which is better than what's available today. So Tropomi's native pixel is 7 kilometers by 7 kilometers. We're publishing a grid of 2 kilometers by 2 kilometers. But we're a business, right? So it's still not as good as what we can do. If somebody really wants to know what's going on behind a 2 kilometer by 2 kilometer pixel, they can call us up and we can sell them data at 25 meters by 25 meters. So that's the latest, and there's lots more coming up. There's taking all that information and turning it into useful information, taking all that data and turning it into useful information for customers. All the analytics of combining our satellites with other satellite data, with ground information, with aircraft information to provide a simple, easily understandable, actionable set of information for customers. That is a whole other discussion topic. And underlying all that is us launching even more satellites. So we have our next satellite ready to go in December. It's GHGSat C2, we call it Hugo. And Hugo is going to launch on SpaceX on December 30th. And we just placed orders for 3 more satellites. So those will be launching in early 2022. And we intend to launch another 5 satellites behind that by the end of 2022, or at worst case, early 2023. So adding capability, adding capacity, adding analytics around all that, there's just so much going on, and we're really excited to be part of it. So Daniel, back over to you.
Thank you very much, Stephane. I can makes me think how lucky we are to get an hour of your time here with everything that's going on there at GHGSat.
I'm happy to do it. Very happy to have the opportunity.
One question in terms of impact. So we now have, this is an open question to you and Bob. What are we seeing people doing based on this data? What actions are people taking, and what impact is it having?
Well, I can jump in first. We've seen the kind of impact that it can have in a paper that we published in just almost a year ago, where we detected a series of sources actually in Central Asia. And we informed the operators of, I'll focus on one in particular, one of those sources we informed the operator. It took about 3 months between when we initially informed them of what we were seeing and a little bit of help in this region from some diplomatic channels, because reaching some of these places is not always easy directly. But with the help of 3 different ambassadors, including the US ambassador, the Canadian ambassador, and the EU special representative for Central Asia, we eventually got that leak shut down. And that one leak was, if we just switch to carbon dioxide terms, 5 megatons of carbon dioxide per year. And that means about 1 million cars off the road per year, just one leak. Yeah. So the kind of impact you can have is dramatic.
Yeah. And now with more satellites and more resolution, that can only increase and accelerate.
Yep, I'm very much looking forward to talking about another case study that we're working on in another place in Central Asia, where operators this time responded within 2 days to our first satellite imagery. And I'm told they're just about to complete their repairs. So those kind of case studies just bring to light the kind of impact this technology can have.
Yeah. And Dr. Kleinberg, what do you think about other? That was really an example of an operator taking action. What do you see on the sort of regulators and investors? What kind of actions do you expect to see going forward now they're armed with more data?
Yeah, and that is an excellent question. And the value of these measurements is not just shutting down those mega emitters, which, by the way, is really very important, and I'm not taking anything away from that at all. But another value is just understanding the scope of the problem for policymakers. So for a long time, greenhouse gases were sort of inventoried by Greenhouse Gas Inventory Project from the U.S. Environmental Protection Agency and other efforts from international bodies. And now we're seeing that those estimates are just far too low, and the problems are far greater than anybody had thought. So getting these direct measurements, whether it be from satellites, which are certainly extremely important, or aircraft and other ground-based measurements, is really showing us that we really have a bigger problem than we thought we had, and that we're going to have to be taking more deliberate and wide-ranging action to really address our climate issues. So that's kind of the bigger picture importance of what Stephane and other innovators are doing these days.
Right. So a real sense of urgency there, given the scale of what you're seeing.
That is absolutely correct.
Right. So just in general, and this is an open question to both of you, what are the remaining gaps? What are the things that really, we won't be able to do with satellites? There are going to be limitations to what we can do. And maybe what are we going to do to fill those?
I could probably jump in first on that one. So no technology can do everything. And so satellites answer part of the need, and Bob did a great job of describing all but many of the benefits that satellites have versus other technologies. But there remains a detection threshold limit here. In our case, we're 500 kilometers from the surface of the Earth. There's only so small a leak that we can see, even with the most advanced technology available today for spot measurements. We're limited to what most oil and gas operators would consider to be fairly large leaks. So you need to complement that with aircraft measurements and with ground measurements. Ultimately, doing everything on the ground is probably the most rigorous way, because you can actually get to within an inch or a few centimeters of a leak and really be able to figure out exactly where it is and how big it is. But to go within an inch or within a foot or within a meter of every single possible flange and valve in the oil and gas world is a colossal undertaking, and let alone going to visit coal mines everywhere in the world, go and visit every landfill in the world, etc. So ground measurements get you part of the way. Aircraft, but they're very expensive and hard to deploy. Aircraft get you another part of the way, but again are still expensive and, as was mentioned earlier, hard to deploy in some parts of the world. And finally, satellites give you, and multiple different kinds of satellites get you that next layer where you can get different resolutions, different detection thresholds. And even some satellite systems are talking about just being parked over a continent and staring all the time. And I think all of those are great complementary sources of data that are required to really tackle this problem for the operators themselves and for regulators and for investors and for all stakeholders.
And I think one of the things bringing not just detection threshold, but resolution that you're able to do is to discriminate what is actually emitting on that tight resolution, because you could have multiple possible sources in the same place, and unless you get down to that resolution, you can't say with any certainty what's actually going on. Is that?
That's right. So California is always a great example of this, where They have large dairy farms next to oil and gas facilities, next to landfills, and trying to figure out which is responsible for what is a bit of a nightmare unless you've got appropriate resolution. So that's, again, part of why we designed our system from the very beginning, to be able to measure facility level emissions and really be able to discriminate one source versus another.
Right. And obviously OGCI is focused on the oil and gas industry, but do you see interest from other industries like the waste management and agricultural interests?
Oh, absolutely. So like I said, in California, their biggest source of emissions is actually from dairy farms. So they are very concerned about how to systematically quantify that and monitor that in a cost-effective way. The next biggest source, I believe, is landfills. I may have inverted those two, but between the two of them, they're biggest sources. And again, there's interest both from a regulatory point of view, but also from the operators. So landfill owners let's just say in developed countries in particular, are very well aware of the potential for gas recovery, which can actually be monetized. They can turn that into a revenue stream, while at the same time reducing the amount of methane vented to the atmosphere. So there's regulatory pushes and economic pulls for that kind of initiative. And finally, there's the same for coal mines. We also have coal mine customers who look for opportunities to put in place what are called ventilated air methane systems. So you capture the vented air coming out of a mine vent, and you turn that into methane that can be sold or used to power the mine to save on other energy sources.
Right. So, Dr. Kleinberg, how do you going forward? How do you feel about the future of this? Are you pretty optimistic that this is going to become widely used by regulators and government? Do you think the uptake is going to happen?
I am optimistic. And, I think, when methane was first regulated by the Environmental Protection Agency in the United States in 2016, there were only 2 approved methods for detecting fugitive methane leaks. And it's remarkable, in the 4 years that has developed, we now have satellites, much more sophisticated ground-based measurements, aircraft, and so on. And one thing that's encouraging, and I think is not widely appreciated, is that in the midst of its sort of deregulation agenda, the Trump administration actually made it easier to validate various kinds of measurements, including potentially satellite measurements, as approved methods of leak detection that are legally acceptable to comply with regulations. So I don't want to make anyone misunderstand. There was a lot of backward and regressive activity in this deregulation agenda, but at least with respect to accepting new technology, we saw some good things, and I would hate to see that go away when in the inevitable recasting of the regulations in the next administration. So I think as long as we keep that in mind, I think we're going to be in very good shape.
Yeah. Well, I think all of us on this call are technologists, and we all believe in to solve these kind of problems, you need to invest in new technology, and then you need the regulatory framework to support the best available technology as it evolves over time. So I think we all totally agree on that point.
Absolutely.
With that, I'm going to wrap up. OGCI Climate Investments is obviously an investor in GHGSat and continue to provide as much support as we can to them moving forward. We really appreciate the work done by Columbia on laying out the landscape and helping all parties understand what's going on in terms of energy policy and regulation. I think in the discussion today, we touched on the fact that satellites are important, but there's a lot of other technologies. So we've also, GHGSat has aircraft technologies. We've invested in Kairos Aerospace, which is flying huge surveys in the US, Canada, and beyond now. We also have investments in Seacops, which is a drone company that can detect very, very small emissions using drones flying around facilities down to a few standard cubic feet a day. So we feel that we're building up a portfolio that's able to perform on all scales and all levels of measurement. So I think it's a very exciting area to be in, and we're making progress. There's a lot more to do, but at least we've accelerated very rapidly in 2020, despite all the challenges of COVID, I must say. I know Stephane would have probably been 6 months ahead of where he is now had it not been for that. But I think it's a recognition of the hard work of everyone that you managed to get. Going to get 2 satellites launched in the middle of a pandemic is really admirable work. So for this specific thing, we've made a lot of progress in 2020. So a couple of things for anyone who's interested. You can go onto GHGSat's website and see their pulse map. You can just view it for free and see what's going on in the concentration of methane around the world. It's an interesting rabbit hole to dive down and try and understand what's coming from where. I think that's fascinating. We'll also be having a more detailed technical webinar on GHGSat technology in December. And their next launch will be at the end of December, and that'll be live streamed by GHGSat and SpaceX. So those are always great to watch. Hopefully they'll launch it and land the first stage flawlessly, as they normally do. So I'd like to thank Dr. Kleinberg, Stephane, and everybody who's working to support those teams in making these technologies move forward. So thank you very much to both of you.
Thank you, Daniel.